So hello and good morning. Today we're going to be looking at graphical insights from the functions in Calc 1. When I think about what are probably the most important kind of base layers of understanding in this course or things that you can take away, it would be this. I think when I think about problems in calculus, I'm thinking of graphs. I'm thinking very visually about these problems and about these functions curves. So even though this will be a relatively short section, this has a lot of impact in terms of your understanding. At least for me, this really shapes how I view things in calc. So let's dive into it, giving a quick introduction. You know, remembering that it is important to have a visual understanding. If we're just we have our heads in tables or in formulas, we can't really see the forest from the trees, so to speak. So, a picture is worth 1,000 words. Graphs are also key in uh, kind of handing off an understanding to somebody who maybe isn't an expert in mathematics or analysis or science. We can still impart a lot of information to someone using graphs. And we're going to just want to recall a few things about the idea of limits, which I know kind of comes and goes, but I said at the beginning of the course was the underpinning of calculus. So it is here back again visiting us. The idea of continuity, right? A function being unbroken, and then derivatives, the instantaneous rates of change. And we'll dive into each of these pieces as we go through. So, how are limits and continuity connected to the graphs of functions? Well, first of all, let's talk about what we mean when we say one-handed limits or one-sided limits. Which we might call the left-hand limit and the right-hand limit, and how that's connected to limits in general. So the left-hand limit is really what we mean is we say this notation here. It's approaching some a. We use the superscript in the with this negative sign that means from the left-hand side, and of a function f of x. I'll also use this notation L minus to say like left-handed limit, so approaching from the left-hand side. And what this means visually, if I'm looking at a graph of a function, let's say it's doing something like this. And we've got some point A that we care about, the limit. When we say approaching A from the left, that means taking x values along the x-axis approaching A from the left and seeing what happens in response in the function f, so in our output. So you can see how we're kind of like turning the dial along this x-axis here, and then we see the response on the left-hand side. This is what we call a left-hand limit, and we see, does this trend towards something? Does this end up heading towards a concrete place, or does it spiral out of control? Does it blast off to infinity? Is there a jump? These sorts of things. Okay, this is what we call a left-hand limit, and a right-hand limit is just the same, but coming from the right. And we use this notation of x is approaching a from the positive side of it, meaning from values greater than it. We call this the right-hand limit. And so, for this, let's say we use, well, we'll just draw a separate graph here. Okay, so similarly, here's my f of x. Point A I care about, and now I'm coming from values greater than A, heading towards A on my input dial, and seeing what the effect is in the output. And if, again, here I've drawn it as if it's approaching some value, but that doesn't need to be the case. But this is what we mean by one-sided limits, and we say that the limit exists so the limit meaning x approaches a without that superscript notation exists if the left-hand limit equals the right-hand limit. This is kind of like a fundamental understanding of limits, that the left-hand limit needs to equal the right-hand limit. If that's the case, that means they're heading towards the same place, and that limit does in fact exist at L. Okay. So how is a function and its graph connected to limits? In this way that I've drawn it here, that, we expect that a function, if it's reasonably easy to draw, at most points, that it's going where it looks like it's going, right? If we scoot along the input, along the x values towards some point from both directions, they're going to be looking like they're going to the same place. And if they're not, that means that we're probably at some sort of discontinuity. Okay, and so we'll unpack that a little bit more specifically in the next one. So if a function is continuous, we know that it means that the limit exists at each point in the interval. All right, so moving more into the idea of continuity and the graphical understanding of continuity, right? We remember the loose definition was that if something's continuous, if you can draw a graph and there's no picking up of the pencil when you need to do so, right? We definitely want to get more fine-grained than that, but that's a good intuitive understanding of it. But what continuity really means at a point and on an interval is it means that the limit exists at some point A of f of x equals f of a at each a. Oh, let me came off the screen here. At each x equals a. So this means at a point and at each point on the interval, it would be continuous if this is the case. So what it means is that the limit exists means it's approaching, right? It's trending towards this point, f of a, and it's defined there so that it doesn't have a hole, okay? It is defined there at each point, and it looks like it's approaching where it's going. So it's kind of got this idea that it's well behaved. It's predictable, okay? So this is that relationship between continuity and limits, is that each function does what it looks like it's going to do when we're looking at it. If we zoom in, we're not going to see any invisible jumps or breaks necessarily. So the types of discontinuities, again, since we're kind of here in this graphing section, I just want to put these down. So what is a removable discontinuity when we're talking about that? That's when we're talking about a hole in a curve f of x. So this is where we call it removable because we could redefine a function where we just plug up that hole, right? And it would be totally the same function everywhere else. So that's what we call removable, and it's typically removable by a factor in a rational function. So here's, we'll call this a removable. A jump discontinuity means that you're seeing a break in the function, something like this, where there's a vertical gap. This happens in step functions. This happens in all sorts of functions that are defined to have this break for whatever reason. Again, you hit something with a hammer. Usually something's motion isn't going to be smooth. There's going to be maybe some sort of jump. So you could see something like this with like an impulse. An infinite discontinuity would look something like this. It kind of comes in two flavors. You could have maybe an asymptote here where the function is blasting off to positive infinity, and negative infinity around it. This is pretty common. Or they could be, heading in the same direction as well. They might be, both heading off to positive or negative infinity around that. But this is what we mean by an infinite discontinuity, or we say it blows up, right? Meaning these values take on either gigantically positive or tremendously negative values. So the function blows up. Something extreme is happening here. And then one that's a little more rare, but it does happen. It's what we call oscillatory discontinuity. And what we mean by that is that a function might start to oscillate faster and faster and faster to the point where you really can't tell in the middle here that, is it this value down here, or is it this value down here, or does it kind of look like it's two values at once because it's flopping back and forth so fast. So again, this can happen if you have a sine function and you have some, maybe an exponential piece in the frequency slot, so it's increasing how fast it oscillates faster and faster and faster. This is what we'd call an oscillatory discontinuity, where it looks like it might be taking on two values at once. So these are kind of the four main things that we can see come up and be problems with a function. Again, from a visual perspective, writing these out algebraically is different, but that's not our focus right now. So some things that will definitely be key in this section for your practice problems and upcoming problem sets is remembering the derivative as the slope of the tangent line. What do we mean when we say that? That if we have a function f, like Mally, you always draw the same function, making it easier on yourself. That's right. So the derivative of is the slope of the tangent line. So at some point a, some point x equals a, that we can, big miss, we can draw a line through it that has the same slope as the curve right at this point. All right, we'll call this the tangent line. And so the derivative being the slope of the tangent line means that, the slope m is what we usually use for lines. M is f prime at a. Okay, so the slope here, the rise over run of this line, this is your dy over dx. That slope is the instantaneous slope of f at this point. So why this is important is because this tells us that for this tangent line's slope, when m or when f prime of x is positive, what do we know about positive slopes of lines? We know that it means that that line is on an increasing trajectory, right? Up y over x, up y over x. So this tells us that f of x is increasing at that place. And when f prime is likewise negative, this tells us that f of x is decreasing. Okay, so when you see a, maybe the function of, you see a function f, when it's increasing, like here, you know that f prime is positive. If it were decreasing, it would be negative. And vice versa, if you saw, let's say instead I gave you the graph of f prime, and we're asking you to, speak to what you know about f. Well, what do we know about f? We know that f prime is taking on negative values from here to here. All right, actually, let me do this in red. It's taking on negative values from here to here, and then positive values from here to here. Right, because we see that these outputs are positive, these outputs are negative. So this tells us that, and maybe we'll call this point A. This tells us that, f is doing something like this, where it's decreasing to a certain point and then increasing away from that point where this is, x equals a. It's doing something like this. All right, and this is my function f. We can pull that from, again, the output of f prime. And what gets confusing for folks is that they start to see, well, maybe, f prime's turning around here, and maybe coming back down, and you start to think, well, that means that f will start to be decreasing. That's not the case, because remember, what is f prime? F prime is the slope of the tangent line. As long as that's just even over 0 by a little bit, that means that f must be increasing. So if the output of this function, f prime, the slope of the tangent line, is above y equals 0, that means that f must be increasing. And just the opposite for if it's underneath the x-axis, sorry, if it's underneath the x-axis, then f must be decreasing. Okay, so this is a very basic but necessary understanding that can be confused based on how we usually read graphs. And there's more to analyze here, but I just wanted to give you this kind of very, very important insight between the graph of f prime and f. If it's under the x-axis, that means f prime is negative, which means it's decreasing, and the other way around for increasing. Okay. So a couple more points here. The relationship between critical points and local extrema. So one comment here is that if we have a graph, all right, what is a critical point? A critical point is a point P where f prime of P is 0 or undefined. Now, a little asterisk here is that this needs to be, P must be in the domain of f. So you can't have a point be a critical point if it's not even in the domain of the function. Okay, that might seem like a silly point to make, but it will actually come up in our example in a little bit. So, what is the relationship between critical points and local extrema? If a function has a critical point, that means, like here, we'll say, let's let this be P1, let this be P2, and my function does something like this. A critical point means it's a point where the derivative, f prime, or the slope of the tangent line, is 0. So that can be the case here and here, where I have obviously a local max. We have a local min. But we might remember that this can also mean something else, which is, let me add on to my picture here and do something like this. That out here, this would also be a critical point. Because why? Because it takes on a slope of 0 here. But this isn't an extrema, right? This is what we call a plateau. Because it was increasing before, and it's increasing after, and so it's not an extrema. It doesn't take on a value that's higher or lower than the function nearby. It's kind of unremarkable outside of the fact that it's a bit of a flat spot. Okay. But this is the relationship between critical points and local extrema. They can be local extrema, but they aren't always. Right? And that's why we need to use the derivative tests or just one or the other to determine that. All right, and then lastly here, what is the role of the second derivative in determining concavity and inflection points? Okay, again, from a graphical perspective. So if we look at, let's say, function doing something like this, and we're at a point A. Actually, let me get a better example here. Let's do something a little interesting like this. And so, right, we'd see it. We have a critical point here. You have a critical point here. And we also have an interesting point in here. This what we call an inflection point. Inflection point. What does that mean? An inflection point means there's a change in concavity. It means it goes from being concave up to down or from concave down to concave up. So how can you tell this about a function? Well, first of all, you can see it from the graph, right? This cupping downward shape. This cupping downward shape to cupping upward. This is concave down and concave up. Not sure why that's happening. So, but we can also get it from our understanding of what f double prime really is. F double prime, right, is really the derivative of f prime of x, right? This is f double prime. And so this is asking you, how is the instantaneous rate of change, or slope of the tangent line, changing or trending? Well, if we look over here where it's concave down, it's cupping downward or decelerating. What can you say about the slopes of the tangent lines as I draw them in as we go? Right, these slopes, as I move this way along the x-axis, are going from steeply positive to flat and then negative. And so overall, those slopes are decreasing, right? And so that's why we'd say it's concave down, or f double prime is less than 0 over here. Whereas on this side, and I'm going to undo some of the busyness of my picture here. So over here, we'd say f double prime is negative. Those slopes are, right, decreasing. And over here, just the opposite's happening. The slopes of the tangent lines are going from decreasing to 0 to positive to steeper. It's concave up. So this slope, how is it changing? It's increasing, so that means the derivative, that second derivative, must be positive. And so when a function is concave up, we know f double prime is positive, and when it's concave down, it is a negative. And this is what we know from the second derivative test. But similar to before, you might be given the graph of f double prime instead of f, and you should be able to pull this insight in the opposite direction, right? Maybe just knowing that f double prime was negative, you could sketch the graph of a concave down function. And likewise, if it's concave up, you'd sketch maybe something that's cupping upward if you're looking to see what the function's doing. This is telling you about like the acceleration of a particle or something like this. All right, and so now a quick example to kind of tie some of the ideas together from this video. So if we looked at the function 1 over x, what does this function look like? Well, it looks like this. Down from positive infinity and trending towards 0 over here, and coming from 0 and blasting off to negative infinity right here. So this is our f of x equals 1 over x. And so we can look at this from the few perspectives that we talked about, noting, where is it continuous? Whereas it continuous means where it's unbroken when we're looking at a graph. But we can also look at the function's formula itself. But here we can see that it's broken at x equals 0, right? We have a discontinuity. What type? We have an infinite discontinuity or vertical asymptote at x equals 0. So this tells us that it's continuous then on the interval from negative infinity up to 0, and we could use this union sign to join the two sets, and from 0 to positive infinity. And so we also want to note that, what does this really mean? Yes, we didn't pick up our pencil, but at every point along the way that's on either of these intervals, from 0 to infinity or from negative infinity to 0, that at each point A that you could call out, that the function has the limit existing at that point, and that it goes there, and that it's defined there. And so that's really what we mean by continuity, and you can do this at every single point. But we see at A equals 0, the limit as you approach 0 from the right, and the limit as you approach 0 from the left. From the right, as we approach it, what happens? Let me get this stuff out of our way here for a second. Oops. As we approach it from the right, it blasts off to positive infinity. And as we approach it from the left, coming in over here, the function blasts off to negative infinity. So since the left limit does not equal the right limit, we say the limit does not exist here. And that's why we can call it a discontinuity, okay? Because the limit doesn't exist. And what do we know about continuity? It has to be defined there, and the limit has to exist. Okay, that's what's needed to draw a line and not pick up your pencil in a mathematically rigorous way. And from the perspective of the derivative, we look at this function. What's interesting about it is that it's actually always decreasing. If you look on the left-hand leg, like you kind of like cover up this side over here and just look at the left-hand leg, you see that it's decreasing as you go left to right. And then if you cover up this piece and you look from left to right, the same thing's happening. It's decreasing the whole way. And so it's decreasing on its whole domain, which means what about f prime of x then? F prime of x must be less than 0 for all x in the domain of f. I'm just using this fancy notation because I'm running out of room. But for all x in the domain of f, f prime must be negative. So how can we confirm this with what we know about f of x? So I'll say, notice this, that if I take the derivative of f of x, which is the derivative of 1 over x, which is x to the minus 1, we get minus x to the minus 2, or negative 1 over x squared. So this is f prime. And what do you notice? From an algebraic perspective, whatever x I plug in here, besides 0, because that's not in the domain, whatever x I plug in here, it's going to get squared, so it'll be positive, and then it's being divided by negative 1, so this will always be negative. So since this will always be negative, that means f must always be decreasing, and that's exactly what we just said we're seeing from the picture. Okay. My whole goal today is to have you kind of connect the algebra to the picture and back and forth. So that's why I might be sounding like I'm repeating myself a lot. I am, and I'm doing that on purpose. So that's the case from the first derivative perspective. And then we can also look at, concavity here. We see on the interval from from negative infinity to 0 on this left piece over here, it's concave down. And over here, it's concave up, right? We're cupping upwards. Here we're cupping downwards. And so, how can we also connect this to the algebra. Well, if we took the derivative of f prime, we'd see that we're really taking the derivative of negative x to the minus 2, which then would be negative 2 times a negative 1, x to the minus 3. Okay. Had an interruption there, but I think we're on the same page here. So we take the derivative, we get negative 2 times that negative. So what do we get? We get a 2 over x cubed, right? 2x to the minus 3. And what we see is that this also lines up with our graph, that when x is less than 0, f double prime will be less than 0, right? It'll be concave down because they'll be throwing a negative number into a cube, which will preserve the negative, and then the whole thing will be negative. And when x is greater than 0, f double prime of x will be greater than 0 because, again, I'm plugging in a positive number. The top and bottom are now positive, so the whole thing will be positive. And so this means, that it's concave up. And this here meant that it was concave down. You'll also see this in a lot of places. Concave up is kind of a made-up term. This is really called convex, and concave down is called concave. I may have said this before, but I just don't want you guys to get confused when you're maybe out there reading other things. And so let's see if there's one more note I had here. Yes, so to note that there's no critical points or inflection points, even though there was a change in concavity. And why is that? Well, it goes back to that asterisk I put in before, why this is kind of a special snowflake of a function, in that x equals 0 is not in the domain of the function, right? What did we say? That it's continuous here. This is the domain of f. It's where it's defined. And so if we had a critical point, it would have to be in the domain of f, and that is not the case here. That x equals 0 isn't in the domain, so we can't call it a critical point. We can't call it an inflection point, even though it is where it blows up. It is where it changes concavity. That technically doesn't fit the description. But this is something that you're going to want to look out for in other functions, right? This is just one. But I think we did a good job of unpacking the different graphical things we'd care about and tying them to the calculus and the algebra. All right, so I hope you found this helpful, and I look forward to your questions and the discussion, and enjoy.